Good afternoon, everyone. This is Daniel Lor, and you are attending the discussion of ESci 114 Laboratory Exercise number 5, which is Faraday's Law. So the deadline for the submission of this laboratory exercise will be on the first week of December. However, as we have agreed during our previous discussion or previous lectures, the last day of submission of your laboratory reports will be moved to December 10. So that is our deadliest deadline. After experiment number 5, we'll still have another exercise, which is molecules and light. So we will be discussing that this week or next week, and the deadline for the submission of that laboratory report will be on December 10th. Also on December 10th, we will be having our final exam, the only exam we have for our laboratory class. I have prepared 2 seat works for this discussion. However, since we have no actual online class for this laboratory exercise, so you may pause the video later so that you can solve on your own the sample problem solvings that we have. Okay, and again, as usual, please do not forget the units, because this is physics. You have to write the correct unit. Okay, so the underlying principle for experiment number 5 is Faraday's law of induction. So by definition, Faraday's law of induction, or briefly Faraday's law, is a basic law of electromagnetism predicting how a magnetic field will interact with an electric circuit to produce an electromotive force, or EMF. Later on, we will just be using the term EMF. Okay? This is a phenomenon known as the electromagnetic induction. This is a fundamental, or this is the fundamental operating principle used for transformers, inductors, and many types of electrical motors, generators, and solenoids. So electromagnetic induction is the process by which a current can be induced or produced. So the synonym for the word induced or induction is produced, or being forced, or being produced. So again, electromagnetic induction is the process by which a current can be induced to flow due to a changing magnetic field. So during your discussion sa inyong lecture, wherein I assume you have already discussed magnetic field or magnetic force, you look at the force experienced by moving charges in a magnetic field. So the force on a current carrying wire due to the electrons which move within it when a magnetic field is present is one of the classic example of the electromagnetic induction. This process also works in reverse, either moving a wire through a magnetic field, or equivalently, changing the strength of the magnetic field over time can cause a current to flow. So, another way to define electromagnetic induction is by differentiating what is electricity and magnetism. Or first, we have to differentiate electricity from magnetism. So electricity basically is a movement of electrically charged particles, but a stream of charge created its own magnetic field. On the other hand, magnetism is something to do with the field of magnetic flux associated with a magnet or magnetic materials. So basically, these 2 principles in physics, electricity and magnetism are very much interrelated to each other. We can generate electricity from the what we call as the generator effect, which is an example of electromagnetic induction. Basically, we have two ways on how we can produce a potential difference, or PD. No? PD means potential difference, or by definition, PD is the difference of electrical potential between 2 points in a wire or 2 points in a conductor. So if you have a wire, which is basically a conductor, and we compute or we detect the electrical potential, so the difference between those 2 points is the potential difference. If potential difference is present, so electric current will flow through your conductor. So the first one is in a wire moving relative to a magnetic field. The second one is a wire experiences a changing magnetic field. So what is the difference between these two scenarios? So the first one, your magnetic field or your magnet is stationary. So ang imong wire mao ang ga-move relative to your stationary magnetic field. Sa ikaduha, your wire will be stationary and the magnet will be the ones moving. So through these two basic scenarios or basic examples, electromagnetic induction is being produced. The wire here, which is stated sa inyong kaning duha ka example, the wire can be any conductor, and if it is a part of a complete circuit, a current will flow. What these examples have in common is a conductor moving through a magnetic field or a magnetic field moving through a conductor, which induces electromagnetic effect. So, during Faraday's time, Michael Faraday made an experiment which leads for him to the determination of the Faraday's law. So it is quite simple. We can easily replicate his experiment with little more than household materials. So during Faraday's time, he used a cardboard tube with insulated wire wrapped through it to form a coil. So, after forming the coil, he attached a voltmeter across the coil, and the induced EMF read as a magnet was passed through the coil. So this is the setup. Basically, this is the setup. So what are Faraday's observations? First, when the magnet is at rest or it is near the coil, but the magnet is stationary. So wala naglihok ang magnet, however, duol ra siya sa coil. So walay voltage nga ma-observe. The second one, if the magnet is moving toward the coil or padulong dito si magnet, some voltage are being measured, rising to a peak as the magnet nears the center of the coil. So inig abot sa magnet sa tunga sa coil, mu peak or mu maximum or padung dito sa maximum ang volume nga sa voltage nga makuha or ma-measure. The keyword is padung dito sa center, because when the magnet passes through the center of the coil, the measured voltage rapidly changes its sign. So mabago ang iyang sign rapidly. And when the magnet passes out and away from the coil, the voltage measured in the opposite direction to the earlier case of the magnet moving into the coil. So if we will plot the induced EMF versus the distance of the magnet sa coil, mao ni siya ang ma-plot natong graph. So these observations are consistent with Faraday's law. Although the stationary magnet, as we all know, might produce a large magnetic field. However, there will be no EMF induced because the flux through the coil is not changing. So ang flux or ang magnetic flux is not changing. So therefore, we cannot produce EMF because there is no potential difference. When the magnet moves closer to the coil, the flux rapidly increases until the magnet is inside the coil. As it passes through the coil, the magnetic flux through the coil begins to decrease, and consequently, the induced EMF is reversed. So these are another demonstrations or actual demonstration. Actually, these demonstrations are the same as what we are going to do for our lab exercise. Number 5. So the left picture, we have a moving a magnet in and out of a coil. The other one, we are moving the wire through a magnetic field. So sa second part, the magnets are stationary. Sa first part, the magnets are moving and our wire is stationary. Both simple demonstrations induce a tiny current in the wire or the electromagnetic induction. There are actually several ways we can increase the induced potential difference and therefore the current flow. First one, moving the wire or the magnet faster. So if we move the wire or the magnet faster, we increase the rate of the magnetic field passing through the wire in which the current is induced. So therefore, mas dako ang potential difference nga ma-induce. Second, using a more powerful magnet. So through this, we can increase the magnetic flux passing through the wire. The third one, using a multi-coil of wire, or meaning mas daghay kanang coils of wire na atong gamiton. So in this case, sa third na case, the magnetic field is the same, or the magnetic field interacting with the coil of wire is the same, but there is a greater length of wire. So meaning mas dako ang ma-induce nga potential difference. These factors are considered when designing like electric motors or electrical generators. So we set up a circuit consisting of an insulated copper wire connected to a very sensitive ammeter. So an ammeter can measure all the electrical variables like voltage, ampere, resistance. So ammeter ang tawag ana nga instrument. So if we bring the magnet near the coil, however the magnet is stationary, nothing will happen. But if we move the magnet in and out of the coil, we can create a potential difference. Therefore, electric current will flow in the coil, or current flow are induced in the coil. It is the change in the magnetic field that the wire experiences that induces the potential difference and current flow in it. So to start with, keeping the poles of the magnet pointing in the same direction. So when the magnet goes in, we should get a blip of an ammeter reading above 0 ampere or positive reading in one direction, and when you pull the magnet out, we also get another blip of an ammeter reading of less than 0 ampere or negative na ang sign sa atong reading. So the reason for these two opposite readings, however, these readings are numerically equal. Pareha sa atong graphs, opposite but equal magnitude. So the reason for this two opposites but numerically equal ammeter readings is that the coil and the magnet are constants. Wala may nabago sa atong magnet, wala yung nabago sa number of coils. But if we change the direction of the motion, we also change the direction of the potential difference and the induced current. Similarly, if we swap the poles of the magnet around, so from negative pole to positive pole ato siyang iswap, which is what we will do sa atong lab experiment number 5, the two readings will be reversed. So the positive ammeter reading will become negative and the negative ammeter reading will become positive. Or in other words, if we change the direction of the magnetic field, we also change the direction of the induced potential difference and the current. So, reversing one thing reverses another. And we only get an induced potential difference with movement. No? So if they are stationary or both of them are stationary, so walay ma-induce nga potential difference. We also have to take note that if we keep on moving the magnet in and out of the coil, we produce a continuous alternating current or kanang AC nga gitawag, alternating current. So this is the principle by which an alternator works. But in the alternator, we keep the magnet stationary and we keep the wire moving. If a current is induced in a coil, Faraday reasoned that there must be what we call as the electromotive force pushing the charges through the coil. However, this interpretation turned out to be incorrect. Instead, the external source doing the work of moving the magnet adds energy. So the keyword here is it adds energy to the charges in the coil. The energy added per unit charge has units of volts. So, the electromotive force is actually a potential. However, unfortunately, the name electromotive force is stuck and with it, the potential for confusing it with a real force. For this reason, we avoid the term electromotive force and just use the abbreviation EMF, which has the mathematical symbol epsilon or lowercase epsilon. The EMF may be defined as the rate at which energy is drawn from a source per unit current flowing through a circuit. Thus, EMF is the energy per unit charge added. Again, the keyword here is added by a source, which is different from the definition of voltage because we define voltage as the energy per unit charge released as the charges flow through a circuit. So again, EMF is the energy per unit charge added by a source. Voltage is the energy per unit charge released as the changes flow through a circuit. So to understand why an EMF is generated in a coil due to a moving magnet, we consider this image here on the right. It shows a bar magnet moving downward, shown by the green arrow, with respect to a wire loop. Initially, if we will count the number of magnetic field lines, kanang red nga arrows around the magnet that is flowing from north to south. So, initially, when we count those magnetic field lines, we count how many? 7. Sa kaning naa sa left nga image. Because the magnet is moving away from the coil, after some time or after delta t, naalam na lang tayo mahabilin nga how many magnetic field lines? Ang nahabilin na lang is 5 magnetic field lines going through the loop after a short period of time, delta t. Thus, when a change occurs in the number of magnetic field lines going through the area defined by the wire loop, an EMF is induced in the wire loop. So experiments such as this one show that the induced EMF is proportional to the rate of change of the magnetic field. Mathematically, we can express EMF as E, or lowercase epsilon, is equal to negative n times delta phi divided by delta t, which is also equal to delta b over delta t, wherein your n is the number of turns, your phi is equal to BA, or the magnetic flux. Its unit is Tesla meter squared or Weber. No? BA, or is the product of B, which is the external magnetic field in Tesla, or Weber per meter squared. And your A is the area of the coil in meter squared. So we can cancel out meter squared in both, even if we either use the Tesla or the Weber unit. And time is in second. The unit of the EMF is in volts. Okay, note that the magnetic field lines that lie in the plane of the wire loop do not actually pass through the loop. No, as shown by the kaning nasa left side nga illustration. So in this figure, the arrow coming out of the loop is a vector whose magnitude is the area of the loop and whose direction is perpendicular to the plane of the loop. So as the loop is rotated from delta 90 degrees to 0 degrees, the contribution of the magnetic field lines to the EMF increases. Thus, what is important in generating an EMF in the wire loop is the component of the magnetic field that is perpendicular to the plane of the loop. Again, perpendicular to the plane of the loop, which is B cos theta. Okay, so we have sample problems here which you can solve in your own homes. So you may pause this video so that you can start solving. But I'll read first the question. So a small 4 mm diameter permanent magnet produces a field of 100 millitesla. The field drops away rapidly with distance and is negligible more than 1 millimeter from the surface. If this magnet moves at a speed of 1 meter per second through a 240 turn coil of length 1 millimeter in diameter, just larger than the magnet, what is the EMF induced? So for our final exam, I would like to see on your answer sheet the following details. So first you have to write the given, or what are the given, what is being asked, or what is required before writing your solution. So from our formula a while ago, what are the given here? So we have the diameter of the wire of the magnet, which is 4 millimeter. Its radius is 2 millimeter. Why do I write, or why do we need to write the radius? Because we can use the value of the radius to compute for the area of the coil. So we also have our external magnetic field, which is 100 millitesla, or equal to 1 times 10 to the negative 1 Tesla. So I chose to convert it to Tesla beforehand so that during our computation, it will be easier for us. N, or the number of turns, is 240. Our delta D is 1 millimeter. So as it is stated in the problem. And our velocity is 1 meter per second. Now, sa atong formula, we also have there our delta T. So we could compute our delta T using the velocity and our delta D, or the change in distance. Again, you may pause the video so that you can start solving on your own. So here is the solution. First, we solve for delta T by using the delta D, which is 1 millimeter divided by our velocity, 1 meter per second. This will give us our delta T equal to 1 times 10 to the negative third seconds. And from that, we can solve for our EMF using our formula, negative N times delta phi divided by delta T, wherein our phi is equal to our B times A. So to compute for the A, we have our pi r squared, wherein our r is the radius of the magnet. As you can see, it should be the radius of the coil. However, it is stated in the problem that the diameter is just larger than the magnet. So we can use or assume that the radius of the coil is just the same as the radius of the magnet, equal to 2 millimeter. So from that, we can just substitute our values, wherein your N is 240 turns, your delta phi is equal to delta B times A, wherein your B is 1 times 10 to the negative 1 Tesla. Your area is pi r squared. Your r is 2 millimeter. We can compute. We can convert that to meter beforehand, so that our unit at the end will follow with what is the standard unit for our EMF. No, because mubalik ko dito, if we will follow these units here, automatically the unit for our EMF is already in volts. Okay, so our EMF is around negative 0.3 volts. Okay, so the negative sign here only signifies the direction of your EMF through the coil of a wire, because as stated earlier, this is a vector quantity. It both have a direction and magnitude. So the negative sign again only indicates the direction of your EMF. Any questions? If you have questions, please write your questions in the comment section below. And for those of you who haven't subscribed to my YouTube channel, please click the subscribe button, like this video, and click the notification bell so that you will be notified. So you will be notified on my future or my next videos. The next question which I prepared is this one. Right with it? Imagine a magnetic field goes through a coil in the direction indicated in the figure. So in the figure, you can see a coil of wire with how many turns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 turns. No? The coil diameter is 1 centimeter, and if the magnetic field goes from 0.020 to 0.010 Tesla in 35 seconds, so what is the magnitude of the induced current? Assume that the coil has a resistance of 0.1 ohms. So given ohms, given the resistance, what else are given? The diameter, which is 1.1 centimeter, the magnetic field, induced current. So what is being asked is the current. or induced current, or I. So from our formula, Ohm's law, our EMF is equal to IR, or V voltage is equal to IR. So we already know how to solve for the voltage or EMF, and resistance is already given. So now we can solve for the induced current I. Again, you may pause this video for you to solve, or so that you'll have time to solve for this problem. Okay, so these are the given. The diameter of the coil is 1 centimeter. Ako na siyang i-convert daan to meter para dili natin maglisod sa atong problem solving later on. Our delta B, or the change in the magnetic flux, is from 0.02 to 0.1 Tesla, or negative ang iyang change. Delta T is 35 seconds. Our resistance is 0.1 ohm, and the number of turns is 16. Atong gihap a while ago, it is 16. So we have to compute for the current, or the induced current I. So we already know how to compute for the EMF using this formula here. And we substitute this derived equation sa atong formula, Ohm's law, and we will arrive to the value of your I, which is 0.0000359, or equivalent to 3.59 microampere. Any questions so far? So if you have questions, please send me a direct message through my messenger account, or through my email, or through the comment section down below. Okay, so that ends our discussion. For the part 2 of this video, we will explore the FET simulation for exercise number 5. So these are my references. See you next meeting. Bye-bye.